Okay, this is tough stuff, what we've been doing here. Some people might argue this is the most important stuff of the semester, though, Chapter 8. It's kind of the heart of Calculus 2. Developing these skills at applying these ideas to real-life problems. Okay? It's tough, but it's important, and it's worth putting a good amount of effort into it. But I struggle with it, too. And like I said, I'm not sure about the vertical coordinate of the center of mass for the triangle there. I got to think about that, I think, after class. You would think it doesn't depend on x because it's in the y direction. Density was a function of x. I got to think about it after class. I think in the spur of the moment. If I try to figure it out, it'll probably take me like 10 or 15 minutes or something. So it's not worth the time. Let's consider this same example, though, a pool with water in it, in a new context, trying to figure out facts about pressure and force on both horizontal objects, whether they're made out of metal or wood or whatever, and vertically placed objects. So you can imagine, I don't know, you can imagine a sheet of metal falling in the water or something. We're going to try to figure out information about pressure and total force from the water on this sheet of metal. Let's go ahead and pretend the sheet of metal, well, maybe we shouldn't pretend it's a sheet of metal. Maybe we should assume it's both the floor and the side of the pool. And ultimately figure out the total force from water pressure on those things. That would be my goal. Instead of a sheet of metal, let's just focus on the bottom of the pool, the floor of the pool, so to speak, and the side of the pool, a wall. So we need some basic information about pressure and force and the relationships. I'm going to continue to use the letter Y for a depth. The book uses the letter H. I think probably many physics books perhaps use the letter H. But I'm going to stay consistent with this picture, and I'm going to think about pressure at depth Y. What is the water pressure at depth Y? It turns out to be the density of water times the acceleration due to gravity times y. Kind of analogous to what we had here. This was the density times the acceleration due to gravity times the volume to give you the weight of the object in the first gravitational field. It's got a weight of a thin slice of water there. This is a similar looking equation. Still have the density of water, which is still 1,000 kilograms per cubic meter. That's the mass density of water. Times g, still 9.8 meters per second squared. The product of these being still 9,800 units would be newtons per cubic meter. Force per unit volume. Y is the vertical distance downward. It's the depth that you're at. That's in meters. So this product is going to be in newtons per square meter. Pressure is a force per unit area. Like on your skin, thinking of your skin as having an area at a certain depth. It would be the pressure you would feel in newtons per square centimeter according to this, though you might want to convert that to newtons per square centimeter. This is in newtons per square meter. It might make more physical sense to you if you convert it to newtons per square centimeter. That'll make more physical sense to your mind. But we will keep the units as newtons per square meter when we do the problem. It's force per unit area. And then the total force on an object sitting horizontally, okay, at a constant depth, is the pressure times the area. in square meters. So that was going to be delta times G times Y times the area of the object when it's sitting horizontally. A thin sheet of metal or the bottom of the pool is sitting horizontally. The total force from water pressure on the bottom of the pool is going to be delta times G times Y times the area of the bottom of the pool. So to find the total force due to water pressure on the bottom of the pool, you don't have to integrate anything. You just do a multiplication because it's at a constant depth. This is an equation for an object where every point on the object is at a constant depth. So, with the case of the bottom of the pool, total force on the bottom of the pool delta times G is again 9,800. Go ahead and put units in, newtons per cubic meter. Y is the constant depth of the bottom of the pool, which is 5 meters. And then the area of the bottom of the pool, it's a rectangle, base times length, 5 times 20, 100 square meters is the area of the bottom of the pool. Well, again, I'm trying to do this kind of thing in my head. It's probably not a good idea. I'm rushed for time especially. 9,800 times 500. 4.9 million newtons. The meters units will all cancel. 4.9 million, 4.9 times 10 to the 6th newtons is the total force of water on the bottom of the pool. Mm-hmm.
So is the pressure supposed to be in newtons per meter squared, so it cancels out?
Where do you see a newton squared?
Well, newtons per meter squared, and the pressure at depth it says newton per meter squared. The product.
I see newtons per meter cubed.
Yeah, but up at the top where you calculated it, you said newtons per meter squared.
That's the pressure.
Okay.
That's not what this represents. This represents delta times G, force per cubic meter. So that is per cubic meter. It doesn't represent delta times G times Y. The Y is the 5 meters there. But what about the side of the pool? You have to do an integral for that because the pressure near the bottom is greater than the pressure near the top. It's not at a constant depth. It's at a varying depth. So here you have to think about thin slices, not of the water, but of the wall. What color should I use? The black. Looking at this left wall up here, and imagine slicing it with thin slices at a constant value of y, of height delta y still. The picture starts to get a bit confusing. Do your best. Our goal is to figure out ultimately the total force on the wall. We can do that by figuring out the approximate force on the thin slices and adding up those approximate forces to get the total force. Let's see if we can do that right at once here, all at once. All right, delta F for the small total force on this thin slice of the wall. Come back to this equation here. The area of the thin slice is easy. The little tougher is the pressure to think about. The pressure comes from this. It's going to be an approximation because the depth is not constant along the thin slice. It's approximately constant. So we have the pressure, delta times G times Y. The Y is the thing that's not exactly constant for all points on the thin slice. It's just approximately constant. That's the pressure at that depth times the area of the thin slice. Its length is 20. Its height is delta Y. Its area is 20 times delta Y. There's the pressure at depth Y. Again, in newtons per square meter. That's units of pressure. This is in meters. This is in meters. That's in meters squared. The meters squared cancel. This is in newtons. Add up these things, you get an approximation to the total force. So you write a summation for the total force. And then you say, hey, that looks like a Riemann sum for the integral of this thing. And that's the integral that you do. Y going from 0 to 5. So the total force on the wall is going to be an integral from 0 to 5 of this function that I circled. Delta times G is 9,800. We got a 20 in there as well, times Y. 20 times 9,800, that's going to be what? 196,000? 9,800 times 20. Y dy. Do this integral, you will get 98,000 y squared going from 0 to 5. 98,000 times 25, a little less than 2.5 million. Units is going to be newtons. By the way, while we were on break, I did have mathematically calculate the other integral. You probably did right before the break. You get 4.9 million. No, excuse me. 12.25 million. The integral. This one we're going to get again 98,000 times 25. 2.45 million newtons is the force on the wall. Smaller than the total force on the bottom. What was the total force on the bottom? 4.9 million? Yeah. In fact, half as much, which makes some sense by the symmetry of it. Okay. As far as the strength of the wall and how well it resists water pressure, it's not the total force so much that matters. I think it's more the pressure. Can it withstand pressures, given pressures at all points? That's the more relevant thing, I think, in terms of construction of materials. Okay, so lots of examples, but I hope you feel like you're generally starting to get the hang of this, even though the details of any one problem may be pretty tough. Mm-hmm.
How does gravity affect the pressure on the side of the wall? Acceleration in the y direction?
Yeah, it's a fact about pressure itself.
It's on the floor.
Top of this page.
It's on the
By your floor?
There you go. It's a fact about the nature of pressure itself, and the book mentions this. It is a bit confusing, but at any point underwater, the water pressure is the same in all directions, even though gravity points downward. It's essentially the weight of the water above a small object that causes the pressure, but that pressure acts the same in all directions. I think you could justify it perhaps by the fact that the water molecules themselves are moving in all directions. So they exert a pressure in all directions related to the weight of water above them. I better not try to justify it more than that, or else I'll get myself in trouble. All right, the last 10 minutes of class here. I want to start a new topic. This topic here, present value and future value of discrete payments. Don't worry, we will probably still do more physics problems because you just can't get enough of these things in terms of really understanding them in 1 or 2 class periods. But I want to start the next topic. So we're transitioning into economics, and a big thing we're going to emphasize next week is combining economics with probability and lifetime random variables, and talking about actuarial science a little bit. Will be our main focus of applications next week, along with some physics. Would you rather have $100 right now or a year from now? Which would you rather have? Come on.
No.
Now, right? I want it now. Why? Well, partially just because we're impatient. Give me $100 now. I need the money now. But partially because you could theoretically take that money and invest it and earn interest. Now, if you put it in a savings account these days in 2016, you might only earn a few cents of interest over the course of a year. It's kind of crazy. But there could be other investment vehicles that give you a better rate of return. So yeah, it's partially a psychological thing. I want that money now. I need it now. I can't wait a year. I'm not patient enough. It's partially because you can invest the money and earn more money later. But maybe you'd be willing to wait if I offer you more than 100. I could say, I'll give you $100 now, or I'll give you $110 1 year from now. You might be willing to wait a year if you got 10 more dollars. If that doesn't seem realistic enough to you, maybe you say, would I rather have $1 million now, or $1.1 million a year from now, or $100,000 more? Probably you convince yourself it's worth waiting, okay? What we're illustrating there is what's called the time value of money. $100 now might be equivalent to $110 1 year from now, or $120 2 years from now. They're equivalent values across time. We call the $110 1 year from now the future value of $100 now. Got that? Say it again. We call the $110 1 year from now the future value of $100 now. Conversely, the $100 now, at the present, is the present value of $110 1 year from now. What connects the two is typically called an interest rate. If you could invest that $100 in an account earning 10% interest over a year, at that interest rate, at 10% interest rate, which is real, real good, of course, $100 now is equivalent to $110 1 year from now. At a 5% interest rate, $100 now would be equivalent to $105 1 year from now. In fact, the compound interest formula can be used to relate these. Though, in writing this formula, at least the initial formula that we write, the compounding only happens once a year, so to speak. The book calls the future value B. It's often called that in compound interest formulas for balance. Sometimes it's called A for amount. Take the current amount, the present value, P, which you can imagine is also being a principal for a deposit. Sometimes that's the reason the letter P is used. Sometimes it represents principal for a deposit. Sometimes it represents present value. And multiply it times 1 plus r to the t power, where r is the annual interest rate as a decimal. So if r is 10%, convert that to 0.1. 10% means 10 per 100. Did you know that? Percent means per 100. Cent is like for century or centimeter. 100. 10% means 10 per 100. That's why you do this kind of conversion to a decimal. So if the interest rate was 10%, you'd convert R to 0.1 before you plug it into that formula. And your formula would be P equals 1.1 to the T power. So this is called the future value. It's called B here because sometimes it stands for a balance on an account. This is called the present value. You might say we use the letter P for two reasons. It is a present value, and sometimes we use it for a principal, the word used for what you deposit now to get a future amount later. But we can think of this in context besides bank accounts, okay? We can think of it as a sort of general theoretical framework that might be different for different people, actually. R might be different for different people. If you are more patient than somebody else is, for you, R might be 0.04, and for somebody else who's less patient, R might be 0.08. They might want more money 1 year from now than you do in exchange for not getting $100 right now. Okay, so theoretically, this could be different for different people, and doesn't have to refer to bank accounts. You can solve this for P as a function of B. This is equivalent to P equals B divided by 1 plus R to the T, which can also be written as B times 1 plus R to the negative T power. These are equivalent equations, so you can find the future value when you know the present value with this equation, and you can find the present value when you know the future value with this equation. So this is in the context where the interest rate is thought of as being compounded once per year. But it's going to often be the case for us, in fact more often for us in Calc 2 here, that we're going to imagine the interest rate as being compounded continuously. This is annual compounding. But again, it doesn't have to be a bank account. And in bank accounts, oftentimes things are compounded quarterly, once every 3 months, 4 times a year. But it doesn't have to be that. For continuous compounding, the relationship looks like this. The future value is the present value times E to the R times T power, where R is the interest rate. When you think of the interest rate as being compounded continuously, you're continuously earning interest. And this can be solved for P as a function of B, divide both sides by E to the RT, and get this. This is the way we're mostly going to think about it, actually, because it's the most relevant for us in calculus. I mean, although we are going to think about it some this other way. You got to look at the problem. Does it say, think of the interest rate as being compounded annually, once a year, or think of it as being compounded continuously? Actually, it's a little funny. You don't have to plug in integer values for t here to use this equation. So it's just different ways to think about the interest rate, essentially, for us. Okay, we're mostly going to focus on this way to think about it, because it's easier to integrate things involving E than it is to integrate things involving 1 plus R to the T. That's why this is our focus here in calculus 2. We're going to ultimately integrate these things. Well, we're about out of time. Let me just point out in the book, I think I'll give you a problem or two similar to one of the book's examples, and we'll end class. I'm looking at problem, or example 1, from section 8.6, page 460. These equations I just wrote on the board on the top of the page, page 460. example one, there's no integration going on there. You're thinking about the context of a lottery. You won the lottery, you won $1 million. Would you rather have that $1 million in 4 payments of $250,000 once a year, starting right now, or the entire amount actually reduced a bit right now? And by thinking about either present values or future values, you can decide which is better for you. Though you have to know what the going interest rate is. Because you have to imagine investing the money that you get if you get it in discrete payments instead of in one lump sum. Okay, so I think I'll give you an example, a problem or two similar to this example. And we'll talk more about it next time.